Okay, so for those of you who have not met me before, I'm from a group in ARM who was formed out of an acquisition from Alinea, so we care about debugging multi-process, multi-thread applications. So I'd like to try and engender some discussion on that today. So in the past, we typically kept a lot of our GDB changes locally, which is a terrible idea. So we started dabbling with looking at how well GDB performs when debugging such applications that represent HPC workloads. So for example, if we just focus on a single compute node that may have maybe 20 to 90 cores or more, and you're running your parallel application on it, which is a mix of threads and processors, and unfortunately you have a bug which only occurs at that particular scale. So we want to use GDB to debug that scenario. Well, when we first started doing this work, we came across a few bugs that we thought we could chew on to begin with. So with the help of Andrew and Stephen, we've managed to make two small, but I think quite valuable changes already. If you set a breakpoint on all your threads and you stopped, and then you wanted to call a function on all of those threads, there was a probability that GDB would just hang. And that's something that we fixed upstream and now is in 8.2, thanks to Stephen and Andrew. If you want to control all your processes, you need to, in some way, attach your debugger to every single one of them. This threw up another issue in that if you did that too quickly, you could end up again with another hang where you had six stops arriving in the wrong window. So you ended up in the next snap, wait one, and you were unable to proceed with your debug session. And that has also been fixed upstream thanks to Andrew and Stephen. Just going to grab some water because I'm drying up. But we've gotten to the point where we wanted to kind of engage the community before we did anything larger, to see how best we could contribute our time to upstream GDB. So there's kind of two ways to control your multi-process application. The first way that we served as well in the past for debugging HPC codes was to attach a single GDB per process, but that comes with a few problems. It's challenging to control all of your processes through a terminal multiplexer because you have so many of them, so between 20 and 90, if not more. This comes with a high memory usage because you end up duplicating absolutely everything. So it's not unheard of to completely run out of memory on your node if you want to try and debug it. The other approach is to use the multi-inferior support. My first attempts at this earlier were incredibly slow. It would take about 17 minutes to attach to all of the processes. But as I learned this morning, there's this fancy new feature called set index cache on, and that solves the problem completely. So we can very quickly attach to many inferiors running on the same node and debug quite happily large HPC applications. I guess one question I would like to ask is if there was any appetite for an external symbol cache. So for example, that would allow you to use one GDB per process, but then back off to, say, a database of symbols rather than relying on having all your processes in a single GDB instance. I remember seeing this as a suggestion on a wiki page somewhere, but I don't know whether anything came of it. I would imagine the preferred approach is to have all of your inferiors within one instance of GDB, and then bake the scalability in there.
For the use case of massive parallel,
Can you hear me? Yeah, I was talking now. Anyway, for the use case of massive parallel debugging, typically you have many instances of the same program.
Yes.
So you can solve this if you can reduce the loading of all the copies to just one copy.
Yes.
One way to get to that is to use a single GDB and then debug everything. And that's where we get to the challenges of actually making GDB able to do that.
Yes.
And we're not there yet. There's work towards that, but there's significant effort necessary still. As you know, I'm working on the multi-target aspect, being able to debug multiple machines at the same time, but on the aspect of loading multiple instances of the same inferior, even if it's locally, you still have GDB loading the same information multiple times. There's been progress in that direction, particularly Tom Tromi has been, he picked up again a project he had started a few years ago of making GDB just load information once and then use it by changing the data structures inside GDB to be, so it used to be that GDB would load the debug information already using the final already relocated addresses, and the symbol tables will contain the final addresses of symbols. And we're moving towards on-demand relocation where we store the base, the offset of the symbol, and then when we need the final address of the symbol, we know the base, the bias, and then add the index, and then we get the final address. But this must be changed in many data structures in GDB, so we're not there yet.
Mm-hmm.
We're going to get there, but not there yet.
That's something we'd like to maybe help with if we can at all. There seems to be some memory reduction if you're using a single GDB anyway, for free.
Yeah, it's interesting for several projects, like for example for Firefox, forks multiple processes, and if you're debugging that system, process is big, and you attach, and then you end up with multiple instances of the same process, and GDB went and loaded the same information multiple times. That's silly. We could just,
do it once,
and much faster. On to the server aspect you mentioned. That's a common request we hear. There are different use cases that would benefit from that. Even at the distribution level, it would be interesting to have a debug server that has the debug information for all the distro, and so that users wouldn't have to each download the debug information to their local machines. You just query the server, it would be maintained in a single place. That would be very interesting.
So that's something that would potentially be accepted in addition to
in my
the
opinion,
work in the
yes.
simple GDB. Yeah. So, thanks.
So even if you come up with your core locally, you don't solve the memory usage issue. It's just
You solve it if all the processes are running in the same binary.
yeah, but that takes Tom's project as well.
Takes what? Sorry?
It requires the Tom's enhancement as well to share between inferiors.
Common symbols. Yeah, right. So either solution we take, it will require work. We don't have a pre-canned solution now.
So the slides about multi-core GDB, how does this scale down to multi-core? Because the example you give there is with processes. So say, for example, you have firmware running on 4 cores. How would you then use the multi-inferior to debug each core, halt each core?
I'm sorry, I didn't quite catch that. I'll come up to you.
I don't think these mics are on, because I'm barely hearing the back there recording.
They're recording. My question was
Sure. My question was about the slide says multi-core GDB here, but the examples are more to do with processes. How does this apply in bare metal when you have, say, for example, quad-core DSP? Would you use the multi-inferior method here? Would that allow you to attach an instance of GDB to each core?
Yes. It would, yeah.
And have you made any progress on implementation, or?
Not at the moment, no. So we currently debug these applications using 1 GDB per process, but we see that as not scaling any further because of the memory. So we're looking to scope out putting improvements into GDB so we can do this within a single instance, or in fact develop a simple server.
To clarify, a lot of our users are HPC national labs, and the 2 dominant parallelization strategies are OpenMP and related libraries, and MPI. So often, as a first pass, our users will try and use MPI on node before investing the time and effort to go OpenMP plus MPI or MPI plus X. So frequently we will find codes that are tuned to run within the memory of one, say Xeon Phi or x86 node or Power or ARM, we do all. And they will try and run the biggest amount of science in a certain amount of RAM and then try and stick a debugger in, and we attach 96 debuggers to 96 MPI processes and get rid of the node.
I would kind of like to go the opposite direction here, because the example I can give here is that we have a quad-core audio DSP, and sorry, I'm from Intel. I'm completely new to GDB, by the way. I'm more of a kernel engineer, and it would be how can we, from user space, we want to debug code on this quad-core DSP running bare metal. I've already got code that we can tunnel through the kernel to talk to, to send the GDB commands to the DSP. But obviously I'd like to deploy a stub on each core. And, I did think about having 4 GDBs, but if there's a better way to do this, then I would like to align that so what you're doing would work for, the small scale as well as the large scale.
So first off, the goal of this meeting is exactly to bring up all the use cases and find commonalities and directions. These folks, they focus on HPC debugging, massive parallel. Some others focus on multicore with a single board, having multiple CPUs and maybe multiple architectures in the same board. But the commonality here is the multi aspect, and expanding from some component only understanding one architecture or one thing and making it possible to debug multiple different things at the same time. For the multi-core aspect, traditionally what people would do with GDB would be, I have a CPU microcontroller with 4 cores, then I would write a stub, GDB small server, and it would expose those cores as threads. So GDB would connect to that small stub and visualize as if it was a process running 4 threads. Nowadays, we are seeing heterogeneous computing, where you have a single board, maybe has like an ARM CPU and 4 accelerators, or we saw with a cell, PowerPC CPU, and then the SPU accelerators. How do we expose this to the debugger? And ideally, we'd have a single debugger debugging the whole thing, because then it allows you to logically set the breakpoint, and the debugger controls everything. Okay, so one solution that I'm aiming to make possible within multi-target work, and I can show up some slides I presented last year about what this means more precisely, is you could have a debug stub for example, an ARM CPU and 4 different 4 accelerators. Have a debug stub for the accelerators, have a GDB server for the ARM CPU. So you have 2 different servers, but you have a single GDB, and it opens 2 connections to different, separate connections, and the same GDB controls both as a single logical entity. That's one solution that I am aiming at to make possible. I don't know if it sounds interesting for you guys.
Yes.
Okay. Jeremy was.
Maybe just to elaborate on the cell case, because that's really directly related. And so the one thing is sort of we can extend GDB, and Pedro is working on it to support these multiple connections and whatnot. But when we did the cell, we sort of did the other way around. We sort of, since we were controlling the full system, we adapted the system so that it could work with GDB as it was at the time, which means that, as Pedro said, as long as you can make your system look to GDB like it is one inferior, which then has multiple threads, and they can have different architectures that's supported today, and that's what we had on cell. Then it would work even with GDB today, right? But that would mean you have to put the logic to actually talk to the different cores into your stub. So the GDB talks to one stub, and the stub controls all the cores and presents every core to GDB as a thread.
reducing the cores should be all different architecture, or should they all be the same architecture?
The cores can be different architectures. You would have to add something in GDB to detect what is what.
Which core was?
Yeah. But GDB today, and that's what we're using on Cell, is able to support multiple different architectures in one process. So.
Yeah, so this is what we do in the RISC-V land for our bare metal. Yeah, for our bare metal multi-core debug in RISC-V land, we have the stub, which is OpenOCD in our case for JTAG stuff. It just pretends like it's one inferior and that each one of the cores is a thread. And it's super buggy, but it works.
So we have a customer at the moment we're working with, and we have a slightly different situation they want to get going. So they have 36 RISC-V cores, and they want to load potentially different executables onto different subsets of the cores, and then and there's a single memory for the whole 36 cores, and they want to debug that as one running system. So we actually take the approach of having each core modeled as a different process, a different inferior, and we use GDB's multi-inferior mode combined with the support for single memory space across multiple inferiors, and we've found that to be, for the setup they have, that's worked quite successfully. So they can load, with some Python wrappers around that, they can load different executables onto different subsets of cores, and then they can break across, across the machine as it's running, and then switch inferiors and debug the different executables, and that's worked quite well.
Yeah, so that's generally how we've been treating it, is that each ELF file is one logical process. There's no processes in the bare metal stuff, of course, right? And then if you have multiple cores running one ELF, then they're threads within a core, and it seems to work acceptably.
Yeah, but we definitely, they want to have an ELF that they've written that deals with processing data coming in, and then they have a different ELF that a different team has written, which is completely separate, which deals with processing the data, and they use shared memory to pass
we have
information around the
basically
system, right?
the same.
So they have these 36 cores, and then they'll say, oh well, 3 of them are going to deal with sucking data in, and 10 of them are going to deal with munging data, and then another set are going to deal with pushing data out, and then some of them will be switched off.
Yeah.
So they can just load all these different ELFs up, and then into one shared memory space. And
that's effectively what we're doing as well. I think the GDB side of things is fine. The OpenOCD side of stuff is where it's messier on our end. But it does appear to kind of work in the bare metal end.
Question for you guys. How about bringing up that system? That's one area that GDB used to have problems, like you connect, and traditionally GDB would figure out all these cores and already represent those as threads. What are you doing? Connecting extended remote mode?
I have a patch ready to go. So it actually works really well. So obviously we have multi-inferior support within GDB, but what we found was that's more geared towards you connect to one inferior and then it forks and your set of inferiors grows. But there's nothing in the data structures that fundamentally stops you having a set of inferiors around at startup time. So we have just a small patch in the remote connection code which fixes it. So when you connect to the target for the first time, you say hi remote end, and it just says, yeah, I've got 36 inferiors running, and the remote end just sticks those all in the data structures, and after that everything's fine. So there is a patch. I just need a test for it. I don't know. So my idea at the moment is I'm going to patch the standard GDB server to allow you to start multiple processes on the remote end. No?
Yeah, I was aware of these difficulties. That's why I asked you. So you can, if to write a test, you can just let the program fork in exec once, and then disconnect, and then reconnect. And when you reconnect, everything's already there, and it's a brand new connection. That's pretty easy that way.
So where I want to steer us was to where the end game is, which is a lot of the problems we've seen with some of the wackier architecture we encounter is the assumption that something either looks like a process, which is a thread of control with its own private memory, or it's a thread, which is a thread of control but shared memory. And if you go back to the Epiphany architecture, that had a mixture of shared memory and private memory. and that's increasingly common as a model. And what GDB is starting to work towards is where you've separated out the idea of the inferior, the flow of control, from the address space that you belong to. And that's ultimately where we need to get to. And for these very parallel systems, we saw it on 36 core. So the 36 core system, we started developing pre-silicon using a very later model, which goes at kilohertz. And then you discover that you're modeling your data transfer, and every core is trying to transfer, here's what my 64-bit register set looks like. And you realize that's an awful lot of bits being transferred across the remote serial protocol before you start up, and then everyone times out because they got fed up waiting. So as you start to get to these very parallel systems that are bare metal, having clean separation combined with caching needs to be the end game you get to. And certainly with the emergence of small, 1,000-core systems coming out, then that's sort of going to become a critical bottleneck.
It's a slightly more prosaic point, but there's an awful lot of work done in the back end for these technical, the multi-inferior support, the shared address spaces. But the thing we constantly run into problems with is things like MI mode, the more user-facing aspects of GDB. Even though these things are technically possible, tooling around GDB is made more difficult by the fact that some things in MI mode aren't present, some of them they're either absent or buggy. So the interface to this, the being able to control deterministically many inferiors with many threads, that kind of thing needs working on, as well as the underlying, the interesting problems, which is, I think, where a lot of our work, we have a lot of patches in this kind of area. And also, well, I'm sure we can talk more about that, but just don't forget the interfaces.
Post him.
So this may be a very naive question coming from someone with little GDB expertise, but given that, why is there a more programmatic interface to GDB, or why wouldn't there be one?
Well, so that's MI mode, right? So there should be a programmatic interface that we find it's incomplete, basically. There are some commands
The MI interface, you can use the standard GDB commands will just work as a stopgap measure to keep going. I guess I don't see any reason why it's supposed to be that way. It's more just like no one's taken the time to completely fill in the MI interface, and so in the meantime we've just said, oh well, if something isn't an MI command, let's try it as a CLI command, and then we just run it. So.
I probably didn't phrase the question as I meant it, but like, how come is there like a C interface instead, or? No?
There's a Python interface and also a Guile interface, scheme interface. The problem is the Python interface is also not very complete for the purpose of an IDE. One aspect completely missing is a proper run control API. So step a thread or continue. So that part is missing. The MI interface is the most time-tested and robust interface for IDEs.
Okay, I'll segue quickly onto the Python stuff. Python API is generated by demand. So, no one has enough time to do all of the Python stuff for GDB. So if somebody wants something, bring it up on the list, because then it'll get knocked up. The other thing, I wanted to ask a question. I don't want to get into really deep problem solving, but it would help if you could explain a limitation of MI, a very simple explanation where it can't cope with these many cores. What specifically you are seeing in the interface?
I mean, this is not a showstopper bug, right? But this is just an example of the sort of place where the mix of CLI interface and MI interface can make life harder for someone programming a controller, right? So we effectively have two control loops, a CLI control loop and an MI control loop. And within GDB, you can have exceptions trigger. and they might get caught at the top level. And there's a print exception method for the CLI, and there's a MI print exception method for the MI. And when you issue an MI command, what usually happens is you prefix it with like a token, like usually a number. So you command 1, do something, and then when you get an exception, it'll say command 1 error, the error string. There's a few places in GDB where halfway through processing a command, we'll catch an exception and say, oh, well, this exception's gone off, but we can actually keep going. So in the middle of GDB, we'll just go, okay, we want to tell the user something's gone wrong, so we'll just call print exception, not MI print exception. And so just in the middle of GDB, you'll get an exception, it'll say error. But because you haven't called the MI print exception, you don't get any of that token associated with that error string. Now, if what's happened is the user controlling that has sent like a series of commands to GDB, so they'll say command 1, do something, command 2, do this, then you just get this, after command 2, you get this error string back. You then have to try and reverse, work out after the fact which command was that error string actually associated with.
Yeah, I understand.
It's clearly not a showstopper, but it's just an annoyance.
It sounds very annoying, to be honest with you. But I don't think that's so much as a design limitation. That's just a bug.
Yeah, absolutely.
Yeah, you know, that should never happen.
I don't think anything. I'm not aware that these guys are necessarily arguing that there's a design limitation in GDB. I think it's more just like there's a lot of issues there that when you start to sort of talk about hundreds of threads going, then it can get hard. Solving these problems, like the driver solving these problems can get harder, and so it'd be better if GDB had these bugs fixed, and that hasn't been a priority before, and maybe it should be higher up on the list.
Okay, thank you for answering my question.
Let me just mention that it's very traditional for front-end developers using MI to find a bug in MI and just work around it. And the thought process is typically, oh, bummer, I found this bug. I could fix it in GDB, but I'll still have to support GDB 7.12 and 11 and maybe 7.2. And before I can rely on the bug being fixed, I can maybe have to wait 5 years. So I'll just work around it because I need to. And then why bother fixing GDB since you already have the workaround? So that's how these things perpetuate.
Yeah, I see that.
And
I've seen that lots of times.
Brilliant that IDE developers come to the community. It's absolutely essential to drive this forward.
But not even just IDE developers. If you are dealing with so many inferiors, you need some programmatic interface with which to control them. Otherwise, it just becomes very tedious. So I often find that I'm writing GDB scripts regularly and Python scripts, even if I'm not using an IDE at all, just to drive it into a particular state to debug a problem.
So I have a data point about. Data being transferred from GDB through MI to some IDE. So we were working on a debugging project for a very customized architecture, and we have to transfer a lot of data from debugger to IDE, almost whole state of the chip. And we were thinking that MI will become a bottleneck, but when we experimented, actually, it really was not a bottleneck. So I don't think so. Like if you have a lot of core and a lot of data, MIE is going to be a bottleneck between like transfer of data from the GDB or any debugger. We were actually using LRDB at that time to IDE.
You're saying it's not a bottleneck?
I know. It's
You're saying MI, so he has a project that requires transferring big amounts of data between the inferior and the IDE. And the assumption was that because MI is text-based, there's going to be marshalling there. It would be a bottleneck, but it turned out it wasn't. Okay. Good data point. Okay. No more questions? Do you have time? So, okay. So, I thought if you had time, I could show you the same slides I showed last year and show you the small progress that has happened. See where we are. Maybe that kicks off some extra discussion.
Yes. Well,
Hey, Joel. Remember when Andreas made the new one? The front page is still using the old one. If you follow the link to the mascot, then you find the high resolution one. I need to fix mine as well. Right. So these are the slides I presented at last year's BoF about multi-target. I'll do this quicker than last year and no demo because it takes a long while. So multi-target is about making GDB debug multiple. You can think of it as GDB debugging multiple machines in the same GDB instance. The groundwork that this requires enables also driving GDB in other directions involving multi things, like host accelerator debugging, coprocessor, maybe GPU debugging. I'm not sure. That may involve instead working via the kernel. That one's pretty clear. Debug multiple embedded boards as multiple inferiors. Last week, when I presented this just 2 days before, someone asked about this on the GDB list. HPC debugging, as this fine gentleman require. And right, so right, we're heading in that direction, starting from single process debugging, multi-threading, multi-process, now multi-target. Internally, last year, this is how GDB modeled things. There was a single list of inferiors. That's still the case. There was a single thread list, including all the threads of all processes. That's still the case in master. That's what I'm working on. I'm changing that. PTID structure was used all over the place when we wanted to transfer information about the identity of a thread. And there was only one target stack, and that it still is. That's something that we need to change. If you want to debug multiple different targets, we need to have multiple instances of a concept in GB called the target stack. Right, and after all this work is complete, we will change to this. The third line is what I'm working on right now. Each inferior has its own thread list. It's not absolutely required for this work, but it makes things simpler and more efficient anyway, because once you have 1,000 nodes and each of them has 1,000 threads, if you want to iterate over the threads of a given process, in the current model you have to iterate over the 1 million threads. Here you only iterate over 1,000. The way the target stack was represented before was each target instance had a pointer to the target beneath, and if you wanted to reuse the target object in different stacks, that would not be possible because you only have one pointer to the beneath target. So the representation has been changed to make that possible. That's the representation change is already in master for a while. And the next step will be to, instead of having a single instance of that object representing the stack, we'll just move that object to the inferior object, and magically you'll have a target stack per inferior. That's the next step after submitting the thread list changes. There used to be a funny concept of the current target, which was a squashed view of the target stack. That's gone, meanwhile, this year. Let's see, the PTID structure. What I meant by remains the same there is in previous prototyping of multi-target, there was an attempt to add an identifier for the current target to the PTID structure. So you would have, PTID currently has LDP ID, thread ID, and process ID. And that experiment added a target ID to the PTID. I did things differently. I kept PTID the same, but I made GDB pass around thread pointers instead of PTIDs whenever that was possible. That just makes more sense because in lots of places we would start with a PTID with a thread, pass around PTID, and then whoever needs a thread would look up the thread for that PTID. So we were losing the thread pointer and then fetching it back. We can just pass around the thread pointer. It's mostly merged to master. Some pieces don't make sense in isolation, will come in later. All right. Maybe not that interesting. Right, so this is pretty much the same as before. Not much big news in terms of user visible features, and that's the thing with this project. Once it's complete, you notice practically nothing, except that you can add a new inferior and connect to a different machine. That's it, and things will just work. Otherwise, there are some limitations, and I haven't addressed them. Like, for example, I'm assuming the remote target works in non-stop mode, and that gives you a synchronous communication channel, makes it logically easier to interact with multiple things at once. These will be things that I want to address, but after the initial version is merged upstream. Last year, I did not have new tests in the test suite, and the test suite was not regression-free. Meanwhile, it's completely regression-free. And I've added new funny tests, like I have a test that spawns several instances of GDB server and several instances of core dump and native process, and the same GDB debugs everything like in a salad, and it just works. I make sure that it keeps working as I change GDB. One significant delay on my one significant project that I didn't think I would have to tackle that happened this year was when I wrote the test, I immediately stumbled on something called the target terminal inferior target terminal hours handling. This is how GDB handles the terminal ownership, whether a process is foreground or background in the terminal that needs to be managed, who owns the terminal, the old implementation assumed, it was clearly assuming it didn't really work properly even with multiple inferiors in the same, even with a single target stack. And run into a bunch of problems. So it took me like 3 months to revamp the whole thing and figure out some design that worked for both multi-inferior and multi-target. But that's all now fully fixed. And as a tangent to this, as I worked in this direction, I ended up going overboard and prototyping, making GDB always start inferiors in a separate session, Unix session. And that gives that means allocating a pseudo terminal for that inferior always, as if you had used the set inferior TTY command. And if you do this, you put the inferior in a separate PTY, and then you make GDB handle the marshalling of input and output between the terminals. This gives you a very, very nice decoupling between GDB's terminal and the inferior's terminal. And that allows you fixing a set of really old bugs that are really annoying. Like, for example, when the inferior prints output to standard output, that output comes interspersed with GDB's output. That's particularly annoying if you're using the text user interface, TUI. So if you have the decoupling, then GDB can control when it flushes output and where it flushes output. You can output, redirect output to some magic window, for example. Or it can allow you to, it also allows you fixing Control C. There are some use cases where you cannot stop an inferior, like when you're debugging like a daemon that forks and creates a new session and then detaches from the session. You can no longer interrupt the process, so it's almost undebuggable. If you with this direction I was heading, that's also fixable. So yeah, I went into a tangent that I spent a few weeks more than I should on that. That's something for later, but I'm keen on getting onto that. Yeah, another piece that went into master relating to all of this was the C++ification of the target ops class. If you noticed earlier in the year, there was a bunch of work around that. It seemed like plain silly refactoring, just converting the target ops structure into a class using proper virtual C++ methods. That was a bunch of boring work because it requires touching all the targets in GDB, and that by targets I mean native targets. If it's a cross debugger situation, you can just cross compile. But if it's a native debugger thing, you need to have access to the host to test it, and that meant like dozens of ports, and most of them were changed, like just assuming I'm doing the right thing. They weren't tested because it's just too many. And just for BSDs, we have maybe like 20 different ports for different OpenBSD, NetBSD, FreeBSD, and then ARM, MIPS, Power, blah, 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 on, and all the combinations. But that's all done. So the next step is, as I mentioned, finishing the thread list per inferior. And then I assume that from that point forward, it's going to be a quick process because most of the infrastructure is in place. The rest is, in terms of code size, is small, actually. So maybe this year, I'll finish it. In terms of user interface, I showed this last year. I actually showed the demo. It's pretty much not much new. This is what we have, same as we have today, right? Yeah, so the only difference is that we add a new column, the one that says connection there. And currently if you add, like there you have 4 inferiors, 3 are running a process. Currently, if you have this situation, all the processes will be running on the local machine. But with this work, we will have the choice of running them on different machines. So in info inferiors, you can have you can see the new column showing you where the process is running. Yeah, new command to list the connections, and this is just a strawman name for the command. It can change when it's submitted upstream. Yeah. Really not much changes. Yeah, right. That's about it. That's the status of where we are. And hopefully next year I'll have no slides, like it's done. I don't know if this brings up any questions or comments or anything.
I have a question. Do you have what plans do you have for additional commands to aid in setting breakpoints on, say, a subset of targets, inferiors, and threads?
So the idea is that you don't need, so when you debug this, it's you notice no difference compared to debugging multiple processes on the same machine. Mm-hmm. You just that's inferior 2, and you set a breakpoint on thread 2.1, right? It just happens that inferior 2 is running on that machine.
Right.
If you want to set a breakpoint specific to that host, you just know that that's inferior 5, mm-hmm. and you set it on that inferior. So far, I haven't even thought of adding like set a breakpoint on that target. Could be possible, mm-hmm. but I just not thought of that.
So less of a question and more of just an observation that we've had. For some of the especially complicated C++ binaries that our clients debug, we've seen things like just setting breakpoints on templated code taking 5-6 minutes just due to the complexity of the symbol lookup. While we do want to move to multiple inferior.
Excuse me, would you speak louder?
Okay, while we do want to move to multiple inferior, it does exacerbate problems of scalability in GDB. So having multiple GDBs, one per process, at least means some things can operate in parallel. Mm-hmm. So a prerequisite for us to use all this good work is to make bits of GDB faster. Mm-hmm. Maybe take advantage of some of Tom's work. So can we make setting a breakpoint on multiple processes faster and mm-hmm. share some of the work, symbol lookups, for instance, that kind of thing. So scalability is starting to become an
Yeah.
issue.
And I kind of see that as independent or orthogonal, because we also experience those problems today if you load multiple processes on the same machine.
Yeah.
So you can already start tackling those. As you mentioned, Tom's work and work related to that.
Your breakpoint work.
Yeah, so in specific, breakpoint one's an example that got upstream.
Yeah, I'm sure we have data structures that are horribly inefficient once you scale up. We have lots of linear walks in GDB that can easily turn into quadratic walks and worse when you iterate over all threads and then do something that requires walking through all threads again. That's pretty common.
Just one remark, sort of, since we seem to be getting rid of the globals, some of those missing globals, maybe at some point we can get there where we can actually use threads in GDB itself to parallelize on modern systems. I hope so. Oh, sorry, it was just a comment saying that given that we are working on eliminating the globals, like this one, we hopefully will get to a state where we can actually start using threads within GDB itself. Because all modern systems are multi-core, so we could take advantage of doing stuff in parallel even within a single GDB session. Yes, maybe. And we're still quite a ways away, but maybe.
It's actually a myth that GDB is not multi-threaded. It actually is.
Yeah, well,
I mean, okay. Not really. But if you like, for example, the Windows port is multi-threaded, uses several threads for handling the TCP/IP, for example. So I'm all for parallelism in GDB. I would love to see that.
Just again a data point about this multi-threaded thing. A few years ago, Apache went into LLDB to do decoding of the symbols in multiple threads. So the guy who did it was from Google, and I was talking to him, and he said like on the Google loads, they saw like quite a big improvement. We did not see that much because like our probably executable were not that large. So yeah.
Oh, okay. Okay.
We don't hear.
He was commenting on how on LLDB side a while ago they went through the process of starting with a single threaded debug information reader, and they converted it to more parallelism using threads, and that how significantly boosted performance.
I don't think, though, with LLDB, and I've only just started with LLDB, until all those threads are finished, you're still in the same space, right? You can't really set, breakpoints across all these symbols until all the symbols have been processed, whether it's one thread or 5 threads or whatever. So maybe it is quicker.
So yeah, you can. There are many ways to split the work between the different cores. You can start with a coarse-grained approach, like you have 10 shared libraries. That's probably no good reason you can't read the whole debug information from head to tail for each shared library in a separate thread, because the data structures will be pretty much independent. There will be global lists of things that need coordination, but that should be pretty much parallelizable. Or you can also experiment. I think Tromi was experimenting with this, of parallelizing within each object file, like for example loading multiple compile units in parallel. It's not clear which way is better. It all depends on data dependencies and contention that may cause. So is this it then? All right, tea time then. Thanks for attending. Thanks, guys.